Welcome back. In this video, I'm going to solve exercises 1 and 3 of chapter 2. Exercise 1 is a very simple and particular case of the Hahn-Banach theorem in R2. And it's a particular case of a more general algebraic lemma. Okay? And we asked this question in the exam some years ago. So the question is very simple. We have a vector space E without any norm, just a vector space, and you have two linear forms or functionals from E to R, such that the kernel of f is contained in the kernel of G, or otherwise stated, if you like, whenever f vanishes, G vanishes. So if f of x is 0, then G of x is 0. We have to prove that G is a multiple of f. So G equal lambda f for some constant lambda. For this purpose, we define the map from E to R2, whose components are precisely f and G. So of course, if each component is linear, then the map is linear. So first question, the point 0, 1 in R2 does not belong to the image of E under phi. And second question, we have to separate 0, 1 and phi of E by hyperplane in R2, and then you have to conclude. Okay, so observe that phi of E, in general, the image of a vector space under a linear map is a subspace. So what are the possible subspaces of R2? We have the origin if the dimension is 0, a line through the origin if the dimension is 1, and the whole plane if the dimension is 2. There are no other possibilities. Now, since phi of E does not contain 0, 1, as we shall prove, then phi of E, it cannot be R2. So it's either the origin or a line. Okay. So the first question is easy because we can reason by contradiction. If 0, 1 belongs to phi of E, then 0, 1 is equal to phi of x for some x in E, which means that 0, 1 is equal to f of x, g of x for some x in E. And therefore, f of x equals 0 and g of x equals 1. But this contradicts this condition because x belongs to the kernel of f, but does not belong to the kernel of g. So this is a contradiction. Okay, so phi of E, as we said, is a subspace. So in particular, it's convex and closed because you are in finite dimensions. So it's either, as we said, the origin or a line. And the singleton 0, 1 is compact and convex, of course. So we can, which is disjoint from phi of E, so we can separate them by a hyperplane, which is automatically closed. So we can find a number alpha and a linear map. I will call it H because f is taken, such that h of 0, 1 is less than alpha, and alpha is less than h of z for every z in phi of E. Okay, we don't need the epsilon actually, because this is enough for us. In most applications, this is enough. And by the way, we don't need the full strength of the Hahn-Banach theorem because the situation is so simple. If phi of E is the origin, then we can, of course, separate the origin and A by a line, and you have so many ways to do that. Okay, and if phi of E is a line through the origin, we can, of course, separate this line in blue here from A by a parallel line. Okay, and we have so many choices, of course, but all the lines are parallel, should be parallel, because they don't meet phi of E. Okay, so now, okay, we have two things here. We already observed that if a map is a linear map is bound from below or from above on a subspace, then it must vanish. So h of z is 0 actually for every z in phi of E. So in particular, alpha is strictly negative. Okay, this is the first observation. Second observation, what is the form of h? H is the equation of a line, so it must be of the form a1, h of x1, x2 is a1, x1 plus a2, x2. Okay. This is, and therefore we conclude, so the first thing is that h of 0, 1, so if you put x1 equals 0 and x2 equal 1, you get a2. And therefore h of 0, 1 is a2 is less than alpha. And so a2 is not 0. Okay. So otherwise stated, the line is not vertical, cannot be vertical. And this is clear in the picture, okay? Because a vertical line will pass through A in this case. And since h of phi of x is 0, this means that a1 of f of x plus a2 of gx is 0 for all x in A. Okay? And as you observed, h of 0, 1 equal a2 is negative. Therefore, we can divide by a2 because a2 is not 0, it's strictly negative. So we get g is minus a1 over a2f, and that's it. So very, very, very easy. Okay, now we move to exercise 3, which is about some further properties of the Minkowski functional of an open convex set containing the origin. So we have to first prove that P is uniformly continuous, that we know that C is the set of X such that P of X is strictly less than 1, but we have to show that the closure of C is the set of X such that P of X is less or equal than 1. So P behaves a little bit like a norm. Okay, it's not always a norm, but sometimes it behaves like a norm. And C, if C is bounded, we know that actually P of X is less than a constant times norm of X in general. We proved that in the lectures, but here we are proving the reverse inequality. So if C is under the condition that C is bounded. Okay. And in the fourth question, we have to show that if C is bounded, then C is homeomorphic to the open unit ball, and C bar is homomorphic to the closed unit ball. And we'll show that the boundary of C is homomorphic to the unit sphere. And last question, we have to prove that C is bounded and symmetric with respect to the origin. Then actually P is a norm which is equivalent to the original norm on E. Okay, so first question, and yeah, the last question actually is just a counterexample. Okay, where if we suppose that C is not bounded, then the two norms are not equivalent. Okay, so we work here actually in the space of continuous functions on 0, 1 equipped with the infinity norm, and we take as a convex set the set of all elements in E whose square norm is less than 1 strictly. Okay, and in this case we can compute explicitly what is P of U. Okay, so P is the norm 2 in this case, but however it's not equivalent to the original norm, and the reason is that C is unbounded with respect to the infinity norm. Okay, it's bound in the 2 norm, but not in the infinity norm. Okay, so first question, uniform continuity. Actually, it's Lipschitz continuity. It's much more. So we pick two arbitrary points x and y in E, and we write x as x minus y plus y, and we apply the triangle inequality because we know that P is sublinear, so it satisfies the triangle inequality. So P of x is less or equal than P of x minus y plus P of y. So if we subtract y, we get P of x minus P of y less than P of x minus y. And of course we can, okay, now we know that by the lecture, P of x is less than a constant times norm of x. So therefore, P of x minus P of y is less than P of x minus y, which is less than m times the norm of x minus y. And now by symmetry, P of y minus P of x is less than m times the norm of y minus x, which is the same as the norm of x minus y. So both P of x minus P of y and P of y minus P of x are less than the same thing. So the absolute value, therefore, of the difference is less than m times norm of x minus y, because the absolute value is either this or this. So this proves that P is actually Lipschitz continuous, okay, a desirable property. Second question, we have to show that the closure of C is the set of x such that P of x is less or equal than 1, and we know that C is precisely the set of x whose image under P is strictly less than 1. We proved that in the lecture. So therefore, in particular, C is contained in this set. Okay. Now, by continuity, since P is uniformly continuous, it's continuous. So this set is closed because it's the inverse image under P of the closed interval minus infinity 1, or if you like 0, 1 closed, because P is bigger or equal than 0. So therefore, and C bar is the smallest closed set containing C, therefore C bar is contained in this set. So this is half of the equality. So now we have to prove the reverse inclusion. So we take a point in the set, so P of X is less or equal than 1, and we distinguish between two cases. Either P of X is less than 1 or it's exactly equal to 1. If it's strictly less than 1, there's nothing to prove, because if P of X is less than 1, then it's in C, and therefore in C bar. The interesting case is where P of X is precisely equal to 1. Okay, now if we go back to the definition or a property, fundamental property of the infimum, the infimum is one of the set that we talked about so many times. So the set of alpha positive such that 1 over alpha x belongs to C. So the fact that the infimum is 1 means that actually there is a sequence in the set converging to 1. Okay? Or if you like, because the infimum of a set, subset of R, always belongs to the closure of the set, as you know, and the same thing for the supremum. Okay, so there is a sequence in the set converging to the infimum. This is really something fundamental. Okay, we call this sequence a minimizing sequence, if you like. Okay, so the fact that the sequence that I call alpha n belongs to the set, it means precisely that 1 over alpha n x belongs to C by definition of the set. Okay, but alpha n converges to 1, to the infimum. So 1 over alpha n x converges to x in the space E by continuity of the fundamental operations. So therefore, the limit of a sequence in a set belongs always to the closure of the set, as we know. So the limit belongs to the closure of C. And that's it. So we took an arbitrary point in this set and proved that it's in C bar. Okay, so this establishes question B. Now we have to show that if C is bounded, then we can find a lower bound of P by a constant times the norm of X. What does it mean that to say that C is bounded? It means that it contains in some ball. So in particular, a ball of center 0 and radius L. So this means that there is a constant L, you can call it R if you like, such that the norm of X is less or equal than L for every X in C. Okay, this is the boundedness condition. Now we take an arbitrary element in the famous set that we talked about. So in the set of alpha positive such that 1 over alpha x belongs to C. If alpha minus 1x belongs to C, by this condition, then the norm of alpha minus 1x is less than L, and therefore, if I divide by L and multiply by alpha, which is positive actually, we get alpha is bigger or equal than 1 over L times the norm of X. But this is true for any element alpha in the set. So this guy is a lower bound of the set, but the infimum is the greatest lower bound. So the infimum is bigger or equal than 1 over L norm of X, and that's it. So very easy. Okay, now an interesting geometric property of convex or convex open sets. So convex open sets in a normal space are always homomorphic to the open unit ball, or any open other ball, because all balls are homomorphic, as you may know. And what is the homomorphism actually? It's given in the question. So this F is just defined by, so the homomorphism, actually the homomorphism is global. It's a homomorphism from E to E, taking the convex set C into the open ball. So it's something even stronger than a usual homomorphism. Okay, it's a homomorphism from E to E, taking C into the open ball, taking C bar into the closed ball, and taking the boundary of C into the unit sphere. Okay, there's a very simple formula for this homomorphism. It's defined by 0 at 0. And for all points different from 0, we have just a very simple formula. It's P of X, the gauge of C, divided by the norm of X times X. Okay. Actually, we can give a geometric interpretation of this. Try to take a convex set like a square and inscribe it in a disk. Okay, so what does this homomorphism is just it's stretching the square to get the disk, and okay, or maybe it's contracting it if the square is bigger. Doesn't really matter. Okay, and we fix the origin in this way. So the origin is fixed. Okay, so how do we prove that F is a homomorphism from E to E? We have to prove that it's injective, it's surjective, it's continuous, and its image is inverse image is continuous. Inverse function is continuous. Okay, so step by step. Why is it injective? We take 2 points x and x prime having the same image under F. Okay, now we have to distinguish between two cases. Okay, so if x is 0 and x is not 0. But we know that P of x, so yeah. So we have we distinguish between two cases. Either the common value is 0 or it's not 0. Suppose that f of x is 0, and so f of x prime is 0. Okay? If P of x was 0, then x is 0, right? Because we established, because P is between a constant times the norm of x and less than a constant times the norm of x. So actually, this double inequality tells me that P vanishes only if and only if x vanishes. Okay, so if f of x is 0, then necessarily P of x is 0, and therefore x is 0. And same thing for x prime. So if f of x is 0, then both x and x prime are 0. Okay. The more interesting case is where none of them is 0. Okay. So we go back to the definition of f of x. The f of x by definition, if x is not 0, is P of x over norm of x times x. And same thing for x prime. Okay, so if we take the norm of x over its norm is 1. So we get P of x equal P of x prime. Okay, if P of x equal P of x prime, we simplify by P of x. And of course, none of them is 0 because we ruled that. And therefore, we get x over its norm is equal to x prime over its norm. And now we apply P to both sides. And we use positive homogeneity of P. P of this guy is 1 over the norm of x times P of x, and same thing for the other one. So once again, we get P of x over its norm equal P of x prime over its norm. So, but P of x equal P of x prime, therefore norm of x equal norm of x prime. And therefore, if we go back to this equation, we get x equal x prime. So that's it. So this proves injectivity of F. Now, surjectivity, you have to prove that for every y in E, there exists x in E whose image under F is y. So, of course, we rule out the trivial case. If y is 0, then, of course, since 0 is f of 0, then the x is necessarily 0, and it's unique because by injectivity. So we suppose that y is not 0. If y is not 0, then P of y is not 0, so we can divide. So we take x to be norm of y over P of y times y. And this makes sense because we are dividing by something which is not 0. And now I prove that this x works. Okay. How do you know that? So now if we apply P, and use homogeneity of P, this is a constant. So get norm of y over P of y times P of y. We simplify, we get norm of y. Okay. And now if we take the norm in this equation, we get norm of x is equal to norm of this guy, which is norm of y squared over P of y. And therefore, f of x, by definition, is P of x over its norm times x. And I replace everything by its value. P of x is the norm of y. And a norm of x is norm of y squared over P of y. Okay. So we replace everything by its value. So as we said, yeah. So get norm of y here, and the norm of x is norm of y squared over p of y. So when we divide, we get p of y divided by norm squared. Okay, so if you do the after simplification, you should get y. Actually, how did I take this? I solved the equation p of x over norm of x times x equal y. Okay, in 2 steps. So when you solve it, you should get this. Okay, now it's very easy to check that this x works. Okay. Now, yeah, so now we have a formula for f minus y minus 1, and which is given by this, by something very similar, but instead of p of x over its norm, I have norm over p of norm of y over p of y. Now, why is f continuous? It's continuous at every point. Okay, why is it continuous at every point, not 0? Because if you go back to the definition of f, which is here, so p of x is continuous, norm of x is continuous, and the identity is continuous. So it's continuous at every point, not 0. And why is it continuous at 0? We have to prove that. We compute the norm of f of x minus f of 0. Okay. For if x is not 0, we get, and f of 0 is 0 actually. The norm of f of x is precisely p of x. So, and p of x tends to 0 as x tends to 0 because of the double inequality. Okay. Or just the one side is enough, because p of x is less than m times norm of x. Okay. So as x tends to 0, p of x tends to 0. So this proves continuity at 0. Okay. And we do similarly for the continuity of f minus 1. So at every point different from 0, it's continuous because it's the composition of continuous functions. And we use the reverse inequality to prove continuity of f minus 1 at 0. So if we go back, if we take norms here, we get norm of y squared over p of y. Okay, so but p of y is bigger than m times the norm of y. So when you simplify by norm of y, we get 1 over m norm of y, and this tends to 0 as y tends to 0. So therefore, f is a homomorphism from E to E. And now we just have to check that it takes C into the open ball and C bar into the closed unit ball. Okay. So, okay, so suppose that x is in C, or we can proceed by equivalence if you like. X belongs to C is equivalent to saying that P of x is strictly less than 1. But P of x, as you observed, is the norm of f of x. So this is equivalent to saying that the norm of f of x is less than 1, which is equivalent to saying that f of x belongs to the ball, open ball of center 0 and radius 1. So this means that the image of C under f is precisely the open unit ball. And same thing for C bar, just replace strict inequality by inequality. And if you want for the boundary, actually, the boundary is the difference between these two. So it's C bar without C because C is open. So x is in the boundary means that x is less or equal than 1, but not strictly less than 1. So it's exactly equal to 1. So this is equal to 1. So f of x, norm of f of x is exactly equal to 1. Okay. So this is really something very remarkable about convex sets. Okay. Okay, that's it. Now, question E. Yeah, we assume that C is symmetric, and you have to prove that P is a norm. Okay. So first of all, we know from the course that P is positively homogeneous. So P of lambda x is lambda P of x for every lambda positive, and you have the triangle inequality. Now, if C is symmetric with respect to the origin, then actually P of minus x equal P of x. Why? Because if you go back to the definition of P of x, the infimum of the set of alpha positive such that 1 over alpha x belongs to C. If C is symmetric, then, and 1 over alpha x belongs to C, then minus 1 over alpha x belongs to C. So the two sets are equal actually. So they have the same infimum. So P of minus x is equal to P of x. Now, we have to prove homogeneity so we have to prove the same thing, but if lambda is negative, we have to put absolute value. If lambda is negative, we write lambda x as minus lambda times minus x. And you apply positive homogeneity, because now minus lambda is positive, so we can put it outside. But p of minus x is p of x, so p of lambda x equal minus lambda p of x, which is just the absolute value of lambda p of x. And as we know, the fact that 0 belongs to C implies that p of 0 equals 0, so we have p of lambda x is equal absolute lambda p of x. Okay, and there is another way to proving that p of 0 is 0, is to use this inequality that you established in the lectures. P, of course, is bigger or equal than 0, but it's less than a constant times the norm of x. So if x is 0, then p of 0 is between 0 and 0, so it's 0. So there are two ways for proving that p of 0 equals 0. Okay, so this proves that. So that's it. So what are the properties of a norm? Actually, there are two. We have the triangle inequality, which is the most important property, and we have homogeneity in the large sense. So p of lambda x is absolute lambda times p of x. And we don't need to check that p of x equals 0 implies x equals 0. Actually, there are two ways to proving this. It's just enough to put lambda equals 0. If lambda is 0, then we get p of 0 equals 0, if you like. Or if you like, you can let lambda tend to infinity, to 0. Or you can use the reverse inequality. So since p of x is bigger or equal than 1 than small m norm of x, then p of x equals 0 implies x equals 0. So yeah. So therefore p is a norm. But what did we assume about C? We assume that it's bounded and it is symmetric with respect to the origin. Okay. Now, and we have the double inequality, so this means that P is not only a norm, but it's equivalent to the original norm. Now, the last question is just a counterexample. What happens if C is unbounded? Here, we take E to be the space of continuous functions from 0, 1, and to R. So we have to give an example of a sequence which is unbounded for the infinity norm. And we can do that in so many ways. For example, you can take the sequence defined by un of t equal radical n over 1 plus nt. So when you put t equals 0, you get un of 0 is radical n. Okay, you can draw actually, so it's a kind of decreasing function, which is radical n at 0. And at 1, it's radical n over 1 plus n. So it's a decreasing function which takes arbitrary large values as n tends to infinity. So of course it's unbounded. And there is another one that you can picture. Actually, are encouraged to plot the graph of this simple function. It's also it's kind of triangle-shaped function. So okay, so it's equal to a radical n when n equals 0, and so it's kind of it decreases from radical n to 0, and then it continues to be 0. So you can plot this. So it's from 0 to 1 over n, it's linear, it's a line, and then it becomes 0. So it's a triangle-shaped function. So here again, its value at 0 is radical n. So it's unbounded actually in the infinity norm. However, the area under the graph is bounded. Okay, so if you compute the integral of the square of un, you'll get something bounded. It's bounded by 1 actually, as you may check. Okay, you do the computations. Okay, so here we have so un belongs to the C, but its norm infinity is unbounded. So C is actually, it's convex, right, and open, but it's unbounded. Okay, and in this case, we can find a very simple formula for P of U. P of U is just the 2 norm that you studied last year. Okay, so it's the integral of the square raised to the power 1/2. Okay, so how do we prove that? Double inequality. So we take alpha in the famous set. So 1 over alpha u belongs to C. This means that the 2 norm of 1 over alpha u is less than 1, which means that norm 2 of u is less than alpha. Okay, so alpha is bigger than norm 2. But this is true for every alpha in this set. So the infimum is bigger or equal than norm 2. Okay, this is one inequality. Now, to prove the reverse inequality, we use the previous question. There is an equivalent. Saying that the norm 2 is less than 1 is precisely means that u is in C. And this is equivalent to saying that P of u is strictly less than 1 by the lecture. So pick an element u, so it's u is a continuous function, and a positive number epsilon. As you may know, the norm, what is the norm of this function? This is a constant here, actually. So we can put it outside. So we get norm 2 over norm 2 plus epsilon. So it's less than 1. So this guy actually belongs to C. So its image under P is less than 1. Right? And now I use the positive homogeneity of P. So I can put this constant outside. And I get P of u over norm u 2 of u plus epsilon is less than 1. Actually, strictly less than 1. Doesn't matter. So that's it. So P of u is strictly less than norm 2 plus epsilon, but epsilon was arbitrary. So if we let epsilon tend to 0, we get the reverse inequality. So P is precisely the norm 2. So it's indeed a norm. But the unboundedness of C proves that these two norms are not equivalent. And this is something that you probably know from second year. The norm 2 and the norm infinity are not equivalent. Okay? And this is the reason actually why. Because this sequence actually is unbounded in the infinity norm, but bounded in the 2 norm. Because C is just the unit ball for the 2 norm. Right? And that's it. So this concludes this exercise where we explored some further properties of the very important Minkowski functional of a convex set. So there is a second part of this. So we shall explore more property actually in the next exercise, in the next video. So thank you for your attention.